Jet propulsion can be defined as the force which is generated in the opposite direction to that of a discharge of fluid under pressure escaping through an opening. The force that makes a lawn sprinkler, similar to the one shown here, rotate when water flows through it is one example of jet propulsion that is readily apparent in everyday life. And the thrust that sends rockets, like this one, into space is another, which is perhaps not such an everyday occurrence. Whatever the form that the device utilizing jet propulsion takes, it is essentially a reaction engine, which operates on the principle of the third law of motion, as stated by the English physicist Sir Isaac Newton in 1687, which is that every action has an equal and opposite reaction. The first recorded use of a reaction engine was by Hero of Alexandria in 250 BC. Hero's engine, a representation of which is shown here, consisted of a sphere into which steam was introduced under pressure. The steam was fed through apertures in the centre of the bearings upon which the sphere was allowed to rotate. Allowing the steam to escape through nozzles in two bent tubes mounted opposite one another on the surface of the sphere created thrust, which caused the sphere to rotate around its axis. It's alleged that Hero invented his engine while he was investigating different methods of opening the doors of a temple in Alexandria. In recent times, one of the first attempts at creating jet-powered aircraft resulted in the development of a hybrid design. An Italian, Secondo Campini, designed a system whereby an external power source, in this case a conventional piston engine, powered a compressor. The output of the compressor was mixed with fuel, the mixture of air and fuel ignited, and jet thrust resulted. Campini collaborated with the Italian aircraft manufacturers Caproni, and in August of 1940 the Campini-Caproni CC-2 flew. Although the Italians were unaware of it, a year earlier than this the Germans had flown their version of a jet aircraft, the Hangar 178. This aircraft was powered by an engine designed by a young German scientist called Hans von Ohain. Despite the relatively sparkling performance for that era, it could travel at speeds in excess of 400 miles per hour, the German Air Force initially paid it scant regard, and it was never produced in any quantity. On the 8th of April 1941, the first official flight of the Gloucester E-2839 aircraft took place at Brockworth in Gloucestershire. Sir Frank Whittle had submitted patents for his jet engine in 1930, but it was not until 1939 that sufficient financial and technical backing was found to enable him to manufacture a flyable version of his engine. The firm of Rover had, reluctantly, initially been contracted to produce the Whittle engine, but Rolls-Royce, who could see its potential, eventually took over development of the engine, one of which is shown here. Rolls-Royce reworked the Whittle design to produce the Derwent engine, an example of which is depicted here. This engine was capable, in its Mark IV version, of producing 2,450 pounds of thrust. Later versions of the engine, capable of 3,600 pounds of thrust, were used to power the Gloucester Meteor F8, like the one shown here, flying at an open day at Royal Air Force Kemble in the year 2000. During a visit to the United States in early 1944, the leader of the Rolls-Royce design team found that General Electric were developing engines capable of producing up to 4,000 pounds of thrust. As a response to this, after his return, he initiated a project which culminated in the Nene engine, which at the time was the most powerful engine in the world, with 5,000 pounds of thrust. Possibly one of the most important but least publicised uses of this engine was its incorporation into the Russian MiG-15 aircraft, which was so effective in the Korean conflict. One critical difference between the German engines used in the Heinkel and the later Messerschmitt 262 and those developed from Sir Frank Whittle's original engine was the type of compressor employed. While the Whittle engine used a centrifugal compressor, similar to the example shown here, the German engines, like the BMW 003 model used in the Heinkel 162, utilized an axial flow compressor, similar in design to the cutaway model shown. Axial flow compressors have several advantages over the centrifugal compressor. For instance, whereas the centrifugal compressor compression ratio is limited to approximately 12:1, when the maximum of 2 stages are used in series, by adding more stages to an axial flow compressor, compression ratios as great as 40:1 can be obtained. The term compression ratio refers to the ratio of the pressure at the outlet of a compressor to that at its inlet. A second advantage of the axial flow compressor, almost as important as the first, is that the mass flow which can be obtained through an axial flow compressor is potentially much greater than the mass flow which can be achieved through a centrifugal compressor. As a consequence of these factors, the development of the early centrifugal compressor engines was subjugated in favour of the advancement of the axial flow compressor engines, which continues today. The principle of the gas turbine engine is basically the same as that of the piston engine propeller combination. They both propel a mass of air backwards. Mass times acceleration equals force. In a gas turbine engine, the mass, m, mentioned in the equation is the air delivered by the compressor. The acceleration in the equation is the difference in the outlet velocity of the air, VO, to that of its inlet velocity, V1, due to the addition of heat energy. Force equals mass times V0 minus V1, which equals thrust. With the piston engine propeller combination, the propeller drives a relatively large mass of air backwards fairly slowly, while the gas turbine throws a small mass of air backwards relatively quickly. Newton's third law states, for every force acting on a body, there is an equal and opposite reaction. In the two cases quoted earlier, the piston engine propeller combination and the gas turbine engine, the force created by the mass of air being thrown backwards and its velocity generate a reaction in the opposite direction, driving the aircraft forwards. It must be remembered that the jet reaction does not result from the pressure of the jet on the atmosphere. In all instances, the resultant reaction or thrust exerted on the engine is proportional to the mass or weight of the air expelled by the engine and the velocity change imparted to it. The working cycle of the gas turbine engine is called the Brayton cycle, after George Brayton, an American mechanical engineer who invented the continuous ignition engine, which was the basis of the gas turbine engine. The Brayton cycle and the working cycle of the four-stroke piston engine, the Otto cycle, are very similar, as can be seen in this diagram. The induction, compression, power, and exhaust strokes of the Otto cycle are each matched by induction, compression, combustion and exhaust stages in the Brayton cycle. One major difference, however, exists in that in the gas turbine engine, combustion, theoretically, occurs at a constant pressure, whereas in the piston engine it occurs, once again theoretically, at a constant volume. Power is developed in the turbine of the engine. Other differences between the piston engine and the gas turbine engine concern the continuous manner in which these processes occur in the gas turbine engine, as opposed to the intermittent procedure occurring in the piston engine. In the piston engine, only one of the strokes is utilized in producing power. The other three are effectively absorbing power, while in the gas turbine engine, the three idle strokes have been eliminated, thus allowing more time for the burning of fuel. This is just one of the reasons why the gas turbine engine has a greater power-weight ratio than the piston engine. The pressure-volume diagram shown here, otherwise known as the Brayton cycle, represents the working cycle of the gas turbine engine in its simplest form. Air at atmospheric pressure enters the engine at point A and is compressed along the line AB. Fuel is added in the combustion chambers, which is signified by point B, and the mixture is burnt, in theory at a constant pressure. In fact, the reduction in pressure shown between points B and C indicates that pressure losses do actually occur in the combustion chamber. The drop in pressure is created by the need to produce the swirl and turbulence necessary for efficient combustion, and this causes a pressure drop throughout the combustion chamber length of between 3 to 6%. Notwithstanding this drop, a considerable increase in the volume of the air is generated within the combustion chamber. Between points C and D, the gas generated through combustion expands in the turbine, where mechanical power is extracted from the energy in the gas stream, and the jet pipe, where the remainder of the gas stream energy provides a propulsive jet as it's discharged. In theory, the gas stream pressure attains a value equal to atmospheric pressure before being ejected. As we previously stated, theoretically combustion in the gas turbine engine occurs at a constant pressure. This is achieved partly through the continuous process of the Brayton cycle, and also by the fact that the combustion chamber is not an enclosed space. These circumstances ensure that there are no fluctuations of pressure in the engine as there are in the piston engine, where peak pressures greater than 1,000 pounds per square inch have to be accommodated. These high internal pressures necessitate utilizing extremely strong and heavy construction in the piston engine, and also, if detonation is to be avoided, the use of high-octane fuels. In contrast, in the gas turbine engine, the use of low-octane fuels and relatively light construction methods are the rule, rather than the exception. The turbojet is a heat engine. The higher the temperature attained in combustion, the greater the expansion of the gases, and hence the greater efficiency of the engine. There is, however, a limit to the amount of heat that can be released into the turbine from combustion. This limit is imposed by the materials from which we manufacture the nozzle guide vanes and the turbine blades. The Germans' inability to produce materials which could withstand the heat of the gas stream was the main problem with the early German gas turbine engines. Because of the poor materials used in the turbine assemblies, the engines would only run for between 10 to 20 hours before the turbine blades suffered meltdown and engine disintegration commenced, usually in a quite catastrophic fashion. The use of modern materials and extremely efficient cooling methods in the nozzle guide vanes and the turbine blades has enabled the use of much higher gas temperatures in the latest engines. This has resulted in the more modern engines having a higher thermal efficiency than their predecessors. Gases behave differently from the other two commonly studied states of matter, solids and liquids, so we have different methods for treating gases and understanding how they behave under certain conditions. Gases, unlike solids and liquids, have neither fixed volume nor shape. They are moulded entirely by the container in which they are held. There are three variables by which we can measure gases: volume, pressure, and temperature. We'll discuss two of the so-called gas laws which are most pertinent to the operation of the gas turbine engine: Boyle's law and Charles' law. Robert Boyle was born in 1627 in Ireland. He made important contributions to physics and chemistry, but is best known for the law which was named after him concerning an ideal gas. Boyle's law states that In a gas which is held at a constant temperature, the volume of that gas is inversely proportional to its pressure, or pressure times the volume equals a constant. This holds true where P is the absolute pressure of the gas, and V is the volume occupied when the pressure is P. This is a reproduction of an experiment carried out by Boyle. He had a calibrated syringe filled with air and deduced its volume. While taking care to retain the temperature of the air inside the syringe constant, he increased the pressure and decreased the volume inside it by placing weights on its plunger, taking readings as he did so. You can see that by multiplying the volume by the pressure, the answer remains a constant. Hence, the product of the absolute pressure and volume of a given quantity of gas is constant, as long as the temperature of the gas does not change. Try moving the plunger up and down yourself to simulate changing the weight on it, and note that the results of P times V always remain a constant. Because of the interest in hot air balloons in the early 1800s in France, Jacques Charles and Joseph-Louis Gay-Lussac made detailed measurements on how the volume of a gas was affected by its temperature. Just as Robert Boyle made efforts to keep all properties of the gas constant, except for the pressure and volume, so Jacques Charles took care to keep all properties of the gas constant, except for its temperature and volume. Charles' law, or Gay-Lussac's law, states that if any gas is held at a constant pressure, its volume is directly proportional to the absolute temperature, or, if stated as a formula, the volume divided by the temperature is a constant. Just as we did to demonstrate Boyle's law, we'll replicate an experiment similar to one carried out by Jacques Charles. If we partially fill a calibrated syringe with air and place it in a container of water, then by increasing or decreasing the temperature of the water, and thus increasing or decreasing the temperature of the air inside the syringe, while taking readings of the volume and temperature, and then dividing volume by temperature in degrees Kelvin, we see that the answer is a constant. Remember that, in theory, the pressure inside the syringe remains constant also. Try changing the temperature of the water for yourself, and notice that the results of the volume divided by the temperature remain a constant. Although both Boyle's law and Charles' law work in theory, we are unable, with existing technology, to make them work in practice. For instance, it's impossible as yet to increase the pressure of a gas without increasing its temperature, because of the adiabatic heating which inevitably occurs. Remember the example which is consistently quoted of how a bicycle pump always heats up when air is pumped into a tire. By using Boyle's and Charles' law together, we get a practical method of determining what is happening to the gases inside the gas turbine engine, where temperatures, pressure, and volume are all changing constantly. With the scientists' usual lack of imagination, they have named the integrated Boyle's and Charles' law the combined gas law. The combined gas law represents the relationship between volume, pressure, and temperature. This may be shown as P1 times V1 over T1 equals P2 times V2 over T2. The three main stages when these conditions change in the gas turbine engine are during compression, combustion, and expansion. During compression, work is done to increase the pressure and decrease the volume of the air. There is a corresponding rise in its temperature. Just as they do in the piston engine, higher compression ratios give higher thermal efficiency and lower specific fuel consumption. Notice that the velocity of the air as it progresses through the compressor is actually reducing. This is required so that when it gets to the combustion chambers, its speed is not such that it will extinguish the flame. During combustion, the addition of fuel to burn with the air increases the temperature, and there is a corresponding rise in its volume at an almost constant pressure. The velocity of the gas flow continues to reduce through the combustion phase, until the end of the combustion chamber, which, due to its convergent shape, initiates an increase in its value. The reason for this will soon become apparent. During expansion, when some of the energy in the gas stream is being converted to mechanical energy by the turbine, there is a decrease in both the pressure and the temperature of the gas, with a corresponding increase in its volume. The changes in velocity over the expansion phase are a little more complicated than in the previous phases. The expansion phase is when the kinetic, pressure and heat energy in the gas stream are being converted into mechanical energy by the turbine to drive the compressor. The turbine is most efficient at converting the kinetic energy in the gas stream into mechanical energy, and in order to do this, the nozzle guide vanes which precede each turbine rotor stage are shaped to form convergent ducts. At the nozzle guide vane stage, the pressure energy, and to a lesser extent the heat energy, are reduced by the convergent ducts, and converted into kinetic energy, which, as you can see, shows a dramatic rise. The turbine rotor following each nozzle guide vane stage reduces this kinetic energy by converting it, and some of the remaining pressure and heat energy, into mechanical energy. Succeeding nozzle guide vane stages will continue to convert the pressure and heat energy in the gas stream into kinetic energy, and the turbine rotor stages which follow them will convert that kinetic energy into mechanical energy. The gas stream is then directed into the exhaust nozzle, where the velocity decreases at the expense of a small rise in pressure. This decrease in velocity assists in maintaining the losses in the jet pipe due to turbulence at a minimal level. Finally, as the gas passes through the sharply convergent propelling nozzle, the duct shape causes a distinct increase of velocity, and the pressure of the stream drops to that of ambient in response to that increase. As the air passes through the engine, various adjustments must be made to its velocity and pressure. For example, throughout the compression stage, the air must be compressed, but no appreciable increase in its velocity can be easily tolerated. Another example, which we've already seen, occurs at the exhaust nozzle, where the pressure of the gas is dropped to that of ambient, and a considerable increase in its velocity results. These changes in pressure and velocity are accomplished by the different shaped passages or ducts through which the air must pass before it exits the engine. The design of these ducts is extremely important, because the efficiency with which the changes from kinetic energy to pressure energy and vice versa occur are reflected in the overall efficiency of the engine. In this example of the use of different duct shapes within the engine, it can be seen that the use of a divergent duct will increase the pressure of the air after it leaves the final stage of the compressor and before it enters the combustion chamber. This air, sometimes called compressor delivery air, is the highest pressure air in the engine. Using a divergent duct here gives a twofold advantage. First, an increase in pressure has been achieved with no expenditure of energy in driving the compressor. Secondly, a decrease in velocity has been contrived, which will serve to make the task of the combustion chamber, in keeping the flame burning, less difficult. This example, which we've already experienced, shows how a convergent duct is used to accelerate the gas as it passes through the nozzle guide vanes on its way to the turbine blades. The torque which is applied to the turbine blade is dependent, amongst other things, upon the rate of gas flow into it. It follows then that the faster we can make the gas flow into the turbine, the more torque we can transfer to the turbine. Logically, therefore, if we convert some of the considerable pressure energy of the gas stream into kinetic energy, it will be more efficient in imparting a turning effect upon the turbine and its shaft. When a compressor and turbine are joined on one shaft, the unit is called a spool. This diagram shows a single-spool axial flow compressor turbojet engine. This type of engine was for a long time considered to be the most useful where an engine with a small frontal area was required, such as in fighter aircraft, where a high forward speed was the main criterion. There are, however, problems with the control of the smooth flow of air through the engine throughout its rotational speed range. More of this later. As it flows from the compressor, the air is fed directly into the combustion chambers, and fuel is added and the resulting mixture ignited. The resultant increase in temperature will cause the substantial increase in volume which is required. The energy required to drive the compressor, approximately 50% of the energy in the gas stream, is now extracted from the stream as it passes through the turbine. The remaining energy in the gas stream acts as thrust, as the gases pass to atmosphere via the end of the jet pipe. This diagram illustrates both a centrifugal compressor turboprop engine and an axial flow compressor turboprop engine. The output from a turboprop engine is the sum of the shaft horsepower developed at the turbine and the residual jet thrust. This is called equivalent shaft horsepower, or ESHP. The major difference between the turbojet and the turboprop in how they handle the generated power is that in the turbojet, virtually all of the energy that remains after the compressor has been powered is used as thrust. Whereas in the turboprop, almost all the energy in the gas stream is converted into mechanical energy to drive both the compressor and the propeller. Only a small amount of jet thrust is available from the exhaust system of a turboprop with an efficient turbine. It can fairly be described as residual thrust only. Apart from this difference, the airflow through the engines is virtually the same in either case. The compressor passes the air to the combustion chambers where the fuel is added and the mixture is burnt, and because of the temperature rise, a substantial increase in the volume of the air is obtained at a nominally constant pressure. The gas is now expanded in the turbines, where a drop in the pressure and temperature is converted into the kinetic energy which is exchanged for the torque used to drive the compressor, or compressors, and the propeller through its reduction gear. The turboshaft engine can be thought of as a turboprop engine where the propeller has been replaced by a shaft. Turboshaft engines can be used to drive helicopter rotors. They can also be used in applications where a compact supply of electrical power is required, their output shaft being attached to an alternator. This is the type of engine normally used as the auxiliary power unit, or APU, on most modern transport aircraft. Most, if not all, turboshaft engines incorporate a free power turbine. A free power turbine is a turbine that is not connected to any of the compressors. This frees the turbine from the constraint of having to rotate at a speed that suits the compressor, and this gives the turbine a much wider operating speed range. The single-spool turboshaft engine illustrated here has a reverse flow combustion chamber system. This allows the engine to be much shorter, stiffer, and lighter than it otherwise would be, but does add the requirement for a centrifugal compressor to be used in the high-pressure stage. This allows for the air to be thrown out radially, in order that it can enter the combustion chamber in the correct direction. Other than this deviation, the airflow is similar to that previously described for the turbojet engine, up to the point where it leaves the first stage turbine. The first stage turbine having converted sufficient energy from the gas stream to drive the compressor, the free power turbine converts any remaining energy to mechanical energy, which is utilized to drive whatever is attached to its shaft. The bypass ratio of an engine is defined as the ratio of the amount of air which is bypassed around the hot core of the engine to the amount of air which passes through the hot core. An engine with a bypass ratio in the region of about 1 or 2 to 1 would be considered to be a low bypass ratio engine, whereas an engine with a bypass ratio of around 5 to 1 would be considered to be a high bypass ratio engine. The engine shown here is a twin-spool, low bypass ratio engine. The airflow as far as the end of the low-pressure compressor is identical to that of a pure turbojet. But then the airflow splits into two. An amount, depending on the bypass ratio, will flow down the bypass duct, and the remainder continues into what is the start of the hot core of the engine, the high-pressure compressor. From the high-pressure compressor, the air follows the usual path through the combustion chambers and into the turbine, before it leaves the hot core and rejoins the bypass air in the mixer unit of the exhaust system. The propulsive efficiency of both the low and high bypass ratio engines is much greater than that of the pure turbojet, at the speeds normally associated with jet transport aircraft. The term propulsive efficiency is explained later in this lesson. The specific fuel consumption of both the low and high bypass ratio engines is also much lower than that of the pure turbojet. The experience which was gained by manufacturing and operating the low bypass ratio type of engine proved that engines which dealt with a larger comparative air mass flow and lower jet velocities could deliver propulsive efficiencies comparable to those of turboprops, and indeed a higher propulsive efficiency than turbojets operating at normal cruising speeds. The advent of the fan jet engine had arrived. This model of a triple-spool front fan turbojet engine shown here represents probably the most successful early example of this type of engine, the Rolls-Royce RB211. The air enters the intake and passes immediately into the low-pressure compressor, more commonly called the fan. Here, its pressure is raised before it splits, to go either through the bypass duct or into the intermediate pressure compressor, the amount going into either depending upon the bypass ratio. The thrust of this type of engine is almost completely dependent on the relatively cold air going through the bypass duct, which has a high mass and relatively low velocity, hence its high propulsive efficiency. The air which passes through to the hot core, which consists initially of the intermediate and high pressure compressors, has a great deal of energy added in the combustion chambers. But this energy is required to drive all of the compressors, which includes the fan. In fact, it is the rearmost turbine, or the low-pressure turbine, which is responsible for driving the front fan by extracting virtually all of the energy that remains in the gas stream. If it's efficient in doing its job, then there should be only residual thrust remaining where the hot gases emerge from the turbine. We previously explained that thrust is the product of mass times acceleration. It can be demonstrated that the same amount of thrust can be provided either by imparting a low acceleration to a large mass of air, or by giving a small mass of air a large acceleration. In practice, the former is preferred, since it's been found that the losses due to turbulence are much lower and the propulsive efficiency is higher. In this graph, the levels of propulsive efficiency for several different types of gas turbine engine will be shown. The highest propulsive efficiency at low airspeeds is offered by the turbo-propeller combination. However, above about 350 miles per hour, the propeller's efficiency drops off quite rapidly due to the disturbance of the airflow at the tips of the blades. In comparison with the turboprop, the propulsive efficiency of the pure turbojet appears quite poor at the lower airspeeds. As the airspeed increases in excess of 800 miles per hour, however, the propulsive efficiency of the turbojet starts to improve beyond the capability of the turboprop engine to match it, and from then on there is no comparison, the eventual outcome being a propulsive efficiency close to 90%. Cruising speeds in the order of 800 miles per hour are at present out of the reach of most transport aircraft, and this fact means that in the mid-speed range, where most of the world's jet transport aircraft operate, there is a niche for the bypass engine, both low ratio and high ratio. The low and high bypass ratio engines, which includes the ducted fan or turbofan engine, have a propulsive efficiency which fits neatly between that of the turboprop and the pure turbojet. By dealing with comparatively larger mass airflows at lower jet velocities, the bypass engine attains a propulsive efficiency which exceeds that of both the turboprop and the pure turbojet at the speeds normally associated with jet transport aircraft. The use of larger and larger aircraft has meant that more passengers can be accommodated in each flight. Thus, air travel has become less and less expensive for the individual. This concept of using large aircraft works well, as long as the aircraft themselves remain serviceable. If, however, one restricting component, such as an engine, becomes unserviceable on a large aircraft, then the expense involved in keeping 300 or 400 passengers fed, accommodated, and happy becomes exorbitant. Engine manufacturers, in an attempt to minimize the financial burden imposed upon the users of their equipment in the event of its failure, have started to use modular construction methods, which facilitate changing sections of an engine rather than the whole engine. This diagram shows how the engine is split into several modules. This concludes the introduction to the gas turbine engine.